All right, so let me begin. And let me start with a result which is perhaps nowadays part of a master program. So let K be any field and consider the corresponding projective line which I want to view as a scheme. Then in the corresponding category of locally free sheaves, there is a very special vector bundle of rank 2 whose opposite endomorphism algebra is isomorphic to the path algebra of the canonical pivot, as an easy computation shows. Then, having such an object f, we can consider the corresponding COM functor. This functor sends f itself to the regular module, is left exact. We can derive a left exact functor. And the point is that the derived functor is an equivalence of triangulated categories. For this, it is important that my object f has no higher self-extension and generates it right. So it is one of the most early examples of results of this form. Nowadays, absolutely standard. And for instance, myself, I like to include it in my master course when I go high enough to triangulate. Right. Maybe a bit less known is generalization of this statement, where I want my base field to be the field of complex numbers, and let me fix a finite subgroup of SO2C. Then, as we know from the course on complex function theory, we have the corresponding action on the projective line by linear fractional transformations. So my group G acts on the projective line, and a result which I would like to introduce in the first line to Helmut Lenzing, also it did not appear in this form in his work, says that the derived category of equivariant coherent sheaves on P1 is equivalent to the derived category of finite dimensional representations of the Euclidean quiver given by the same Dynkin type delta as the group G. So Lenzing shows another way to state this result. In this form, you can find it in the work of Kirillov and slightly more generally in the work of Lish. Now let me explain what do I mean when I say G is attached to a Dynkin diagram. So simply less Dynkin diagrams, so it's important here to stress it. My diagrams are of type AD. Are actually parameterized by triple natural numbers satisfying this property. And finite subgroups of SO2C were classified by Felix Klein. And in the course of classification, one actually sees that such subgroups up to conjugation are described by the same pattern. So for classification of finite subgroups of SO2, one proves first then there are at most 3 orbits with non-trivial stabilizers. Then we'll look what is the order of the stabilizer group. It is ABC. Then one has to check that this inequality is true, and then that parameters ABC determines the group. So it's a possible point of view on the classification of finite subgroups of SO2. So there is a statement for derived categories of equivariant sheaves on P1, a beautiful result, of course. But there is one thing which might look like irritating. So when we speak about Van Dynkin diagrams, so we take extended Lincoln diagrams. So here you see black points are non-extended ones, and the 1 point more there are affine Lincoln diagrams. But it is not the complete list. So first of all, there are some extending affine Lincoln types which are missing, which come from non-simply laced diagrams. But another thing is that not affine Lincoln diagram is an extended one. So it is actually a very basic fact, which I learned relatively recently. And one of the reasons that pictures are a bit irritating. But the fact is that there are also other affine Lincoln diagrams which are not extended ones. So actually, in a drawing like this, one wants to say that there is a unique imaginary root. It can be written as a sum of simple roots, and there's a theorem that in such a decomposition, one simple root occurs with multiplicity 1, and it is the white point. So it is the meaning of the drawing. But the diagrams below are not extended ones, so anyhow, so they do not appear in the Mackay correspondence with equivalence of Lenzing, which I showed in the previous slide. And one may wonder why they are missing. So we might see that finite subgroups of SL2 form a fundamental pattern, but apparently it is not so fundamental enough. So what is going on? Well, the answer to this question is given by the concept and the theory of exceptional hereditary curves. So this may be a motivation of the whole story. And the fact that not all affine Lincoln types arise in this way bothered people in the representation theory since the middle of the 80s. And Lenzing in 1998 discovered another generalization of the tilting equivalence for the projective line, namely, let us work over real numbers. And over real numbers, we can take such a conic. We view everything as schemes. And we know that a conic is a projective line if our field is algebraically closed, but if not, then not. So equation x squared plus y squared plus z squared actually has no solution, but still we can take the corresponding scheme. We can speak about vector bundles, coherent shifts. So it is a reasonable category. And the result is that we can consider the following algebra lambda. So here H is a division algebra of Hamilton quaternions. And you might guess that I would like to say that the derived category of coherent shifts on my conic X is equivalent to the derived category of finite dimensional lambda models. So what is perhaps interesting about this example, so when I started my academic career and learned about representation theory of algebras, so I grew up in a belief that any finite dimensional algebra is a path algebra for clear with relations. So it was a paradigm I believed all the time. So maybe at some moment I became aware that one has assumptions on the base field, but I was tending to ignore it. But here it's actually the point. So we have the algebra lambda. So it is a hereditary algebra, but it is not a path algebra of some quiver with relations. Because for this algebra, we have a simple module whose endomorphism algebra is algebra of quaternions, and we do not have it for path algebras of fields. So maybe to comment, so what is lambda? So it is a hereditary algebra, tame. Its Lincoln type is one which was on my list on the previous slide. the so-called type A to 2, a Dynkin type which is not extended one. To help you to understand what is lambda, maybe it would be helpful to look what happens with lambda when I pass to the algebraic closure. And we know that quaternions multiplied with C leads to the algebra of matrices of size 2 by 2. So tensoring with C, we get an algebra which is not basic. But up to Morita equivalence, we can easily see it is a pass algebra of the conic field. So the algebra lambda above is a non-split form of the pass algebra of the conic. But after all, it's not so surprising because I have a conic, so if I pass to complex numbers, it's a projective line. But over reals, it is something else. And this observation led Lenzing to a conclusion that the problem that not all Dynkin types show up is due to the fact that we want our base field to be algebraically closed, which is, for many cases, an unnecessarily strong assumption, which we perhaps have to drop. All right, so Lenzing proceeded in the following way. So first of all, it was already known at the late 70s how to think about tame hereditary algebras in general, so the arbitrary fields. And the basic pattern is the following. I want to study hereditary algebras of the following shape. So F and G are finite dimensional division algebra over K. And in order everything to work, W has to be Fg bimodule. So if F is a bimodule, then we know how multiply. So it is a decent algebra. And then there is a condition which might look a bit strange. So I want this assumption on the dimensions of my bimodule over both skew fields. But it is precisely the assumption fixing representation time. So if the product of this dimension is less than 4, we are in a finite type, and otherwise we are in a wild type. So one can show it. So this algebra is hereditary and also tame. And it is maybe the beginning of the story if we want to take hereditary algebras as a primary object. Representation theory of tame hereditary algebras was very intensively studied by Love and Ringel late 70s. And in particular, they showed many structural things. So they provided qualitative classification of corresponding representations, saying that there are 3 types: pre-injective, regular, and post-projective. So regular representations are most difficult to classify actually, but post-projectives and pre-injectives, the corresponding indecomposable objects are described by the dimension vectors. The dimension vector is a real root. And well, there are many results which make the representation theory of these algebras very well understood. However, here I want to draw your attention that if we work on an arbitrary field, so the representation theory of algebras is no longer a linear algebra. So it becomes more complicated. Also, Euclidean weavers, so they are interesting and complicated enough. And then one can take in the derived category the corresponding subcategory. So actually, this Koch X is a hat of an inappropriately taken T structure in the derived category, defined by some torsion pair. But pragmatically, one can take it as a definition, and one gets some category, abelian one. And actually, I'm not sure to whom one really address this result, but I think it's fair to say Lenzing was one of the first scholars who looked at categories of this sort. And the category defined in this way is abelian, hereditary, has a finite dimensional X spaces, and of course still linear over K. So derived equivalent to the original derived category of lambda models. But what makes it special? In the derived category, we have a surfing up to shift, Auslander right and translate. And it's an autoequivalence, and we might put a wish that this autoequivalence preserves Koch X. So let us wish it. So it is what we want, and recall that tau is an autoequivalence which provides this version of the subline. Then the constructed category has these properties, and then Lenzing and later other scholars, in particular Dirk Cousin, worked on categories of this sort, saying these are categories satisfying some list of axioms. In this slide, I would like to quote axiomatic approach to exceptional hereditary curves. So here, curves arising in this way are still time. So it is a domestic case. But one can generalize this approach to define exceptional hereditary curves in general when we replace lambda by a canonical algebra. However, I must say I was never happy with an approach like this, because it's a bit a philosophical question, a question of taste, what is primary and what is secondary. So if we accept that hereditary algebras or canonical algebras deserve to be viewed as a primary object, then it is a possible point of view, but the resulted theory misses geometry, and it is therefore not so easy to digest. Non-commutative algebraic geometry became popular at the end of 90s, and at that time it also became a tradition to call everything what does not fit in the usual paradigm of algebraic geometry, non-commutative space or non-commutative curve, which is, on my mind, not really a good thing. So we should not use substitution of concepts. So I still wish to have some geometry in this story, and it's actually what this talk is about. So let's do geometry a primary thing, because I think it simplifies the understanding of the whole picture. Because we not only want to study these categories, we also want to do something. And hint that some geometry arises goes to the fact which says that if we take the subquotient of the category of coherent shifts modulo the full subcategory of shifts of finite length, then it is a semi-simple category, and it is a category of well, actually vector spaces of a some skew field L, who has a center, and its center is the field of rational functions of a curve of genus 0. So the first result of this form was obtained by Will Crowley-Bove, but not in this way. So this result is kind of a folklore. And I know that Andrew Hubery and Henning Krause have a book project. One of the topics is the theory of time hereditary algebras. They put a lot of efforts to prove results like this in a systematic way. So when we speak about time hereditary algebras of arbitrary fields, then a lot of things become significantly more complicated, and elements of algebraic number theory suddenly starts to play a role. And in representation theory, we were not used to that. So we did not use any number theory, and we're still alive, till now at least. So now going towards non-commutative curves, I want to introduce first a local notion, which is the notion of the classical order. So a classical order is a ring, and I want its center to be reduced. Excellent. So please don't worry about the meaning of the word excellent. So most rings coming to your mind would be excellent, and this restriction just removes some pathologies. But third dimension one is important. So I want my algebra to be finite over the center, torsion-free, but I also insist that the rational hull of A is semi-simple. So if I have an algebra over R, I can pass to the total field of fractions K. I get an Artinian ring. I want this ring to be semi-simple. So if I have it, it is an order. A typical example, also relevant for the final part of my story, is given by the setting when I have a Dedekind domain and a finite group acting. And if I assume, well, the usual Mashka setting, it's order which is invertible in my ring, first of all, I can prove that the ring of invariants is Dedekind again. My ring D is finite over R, but I also want to talk about the skew group product. So it is a certain ring. It is free, D is free over A. The rank is the order of my group. And here is a definition of the multiplication in my ring. Then A is an order. And it is a very important example of an order in the above sense. So the center of the skew product is a ring of invariants. The rational hull is algebra of matrices over the quotient field of. Okay. So to give you some intuition about orders, so again, I recall the definition. Let me take a Dedekind domain again and any ideal I. Then I can take this ring of matrices of size 2 by 2. Obviously, I can multiply elements of A. And here there are two cases. If my ideal is non-zero, then the rational hull is the algebra of matrices. And I have an order in my sense. But if I is zero, then the rational hull is not semi-simple, and I want to exclude it from my geometric setting. All right, so now I think I am ready to globalize this notion, and I want to define your non-commutative curves in the sense I want to use in my talk. So a non-commutative curve of a base field is in its space, where usual x is a commutative curve. So however, I want to exclude nilpotence. So excellence, again, to exclude pathologies, reduced, well, it is easier to do. Well, equidimensional, I do not want components of dimension 0. But the structure ring is a sheaf of orders, which is a coherent sheaf of OX models. So if I have a sheaf, I can look at local sections, and I want that local sections of R over any open set is an order in the formal sense. So I want R to be coherent. So if I have it, then it is my non-commutative curve. And I can speak about the corresponding category of coherent sheaves. So if I say that the center of of any stock of R is a structure sheaf my central curve, I call my non-commutative curve central. If all orders are maximal, then I call non-commutative curve homogeneous. Maximal order is automatically hereditary, but not vice versa. In what follows, I will talk about homogeneous curves and hereditary. So here is a condition. So one can actually prove that without loss of generality, one may always assume curves to be central. So if they are not central, they can be centralized. So I have just to replace x by some bigger curve, I can achieve centrality. Some lemma one can show with some inputs. I also want to introduce the concept of projectivity. So when my central curve x is complete, so meaning integral proper, well, basically I want to have projective and irreducible. So then I call the non-commutative curve complete. And in this case, I can speak about the field of rational functions of my central curve. And I can also take the rational curl of my non-commutative sheaf R, which is a central simple algebra over the function field. And I have it because I assumed I work with orders in my sense. So I impose this condition of semi-simplicity, and I want to have this non-commutative function field fx because it is an important invariant non-commutative algebraic geometry. So when I speak about non-commutative algebraic geometry, still it should be geometry, and only a little bit non-commutative. And if I take this non-commutative function field f, it defines me the class in the Brouwer group of methods. So to remind you, Brouwer group describes central simple algebras over this field up to Morita equivalence. It's important group from algebraic number theory, and it shows up here. And when I mean number theory starts to matter, I mean Brouwer groups start to play a role in representation theory. We try to work over fields which are not algebraically closed. Okay, so it's again the definition from the previous slide, so nothing new. Now let me comment it a little bit. So what simplifies if I say my field is algebraically closed? So in this case, there is a theorem of Zen, saying that the Brouwer group of a function field is always zero. So it's a significant simplification of the whole story because it implies that the non-commutative function field is the algebra of matrices over K. And if K is not algebraically closed or not, then the whole story is much more interesting. And it is actually one of the reasons why many patterns simplify when K is algebraically closed. And Brouwer group is zero and many things are easy. Well, now let me start to discuss the first class of non-commutative curves of interest, namely those ones which are called homogeneous. So homogeneous or regular, so I'm still undecided which terminology is better. The assumption is that for my structure sheaf A, all stocks are maximal orders. So why homogeneous? What is the meaning of the word homogeneous in this setting? Well, first of all, locally, a maximal order is always hereditary, and its center is a Dedekind domain. Moreover, if you want to study modules of a maximal order, then assume we are in a local situation. So assume that the center is local, then A is semi-local. If A is semi-local, we can take the Jacobson radical J, and then one can prove that finite length modules, which are indecomposable ones, are quotients of I modulo the power of the radical. So the same thing as we have for discrete valuation rings, but now in a non-commutative setting. So here, however, one has to assume that we have an order in a skew field. So if not, one has to rephrase it a little bit. But from the point of view of representation theory, the result is the following. So if I have a homogeneous non-commutative curve, the central curve is smooth, and Auslander-Rayton components, the category of torsion shifts, are all homogeneous tubes. So representation theorists have seen tubes many times. So it is a setting. So it need not be so in general for arbitrary non-commutative curves, but for homogeneous ones, it's the case. Homogeneous tubes are well known in representation theory. If all tubes are like this, then our curve is homogeneous. Now, let me state the following result, which is due to Artin and de Jong. So Artin here is Michael Artin. So those who contributed to foundations of algebraic geometry together with Grothendieck, he introduced catalytic homologies, many things, but he was also a pioneer of non-commutative algebraic geometry. And together with Johan de Jong, so I started to write a manuscript, which unfortunately remained unpublished. Also, many results in that work are really foundational. And one beautiful result one can find there is that given two homogeneous curves, they can be non-isomorphic as ringed spaces. But we are rather interested in the corresponding categories of coherent shifts. And the categories are equivalent if and only if central curves are isomorphic, but also isomorphic in the way that they identify the corresponding classes and properties. So two categories corresponding to homogeneous curves are equivalent if and only if this is true. And now we summarize. The classical algebraic geometry tells us that a regular projective curve of a field is described completely by its field of rational functions. So it's very classical geometry, but being non-commutative and working with homogeneous curves only, the result is that to define such a curve up to mate equivalence, you have to specify a function field, so a field of transcendence degree 1, and an element in the Brouwer. So it is a pattern describing homogeneous curve. And since this pattern is so nice, resembles the commutative case, so one can also call such curves regular. However, I tend to the terminology homogeneous because regular is very overloaded. Now in mathematics, homogeneous still has a more precise meaning. Now I am interested in curves which admit a tilting object, and they are called exceptional. So in principle, an exceptional curve need not be hereditary. There are enough interesting non-commutative curves which are exceptional but not hereditary ones. But let's speak about homogeneous curves first. So if we have a homogeneous curve, then the central curve has genus 0. And it means actually it is given by a conic. So another name for such curves is Brouwer-Severi curve. So a geometrically connected curve of a K of genus 0. Smooth. So and characteristic 2 is an assumption to write a normal forms. Please do not bother too much about this. And in the already aforementioned work of Lenzing, it was proven that there is a tilting object whose tilted algebra has this beautiful shape that we have to skew algebras F and G and attain bimodule double. Bimodule with restriction on dimensions with respect to that. Okay, so what I want to tell you now, right? So to define a homogeneous curve, I have to specify a central curve and a Brouwer class. And it was a bit a surprise for me to see that not any class eta actually defines a curve with a tilting object. So it defines some homogeneous curves. This curve has tilting objects if we pass to algebraic closure, but it need not have a tilting object before going to the closure. So if the class eta is 0, then such curves are always exception. So and the statement is, if I have an arbitrary commutative scheme X given by this conic, there is always a tilting bundle in the corresponding direction. Well, now the next thing I want to discuss concern exceptional hereditary. Curves here are hereditary, but all tubes are so far homogeneous. It need not be the case in general. So how should we think about arbitrary, hereditary, exceptional curves? So for this, I again have to remind you the locals here. I have to explain you what is a description of hereditary orders. So to do it, let me start with a discrete valuation ring. And actually, I think it's better to assume ought to be complete for things I'm going to tell you next. But intuition is formal power series and formal Laurent series over the Now, firstly, let me take some finite dimensional central division algebra over such field L. And if K is not algebraically closed, then there are non-trivial skew fields of this form. Then F defines a maximal order A. So here in this line, F is a choice, but then A is determined by F. So actually, so my A is so well, I think it's so the point is all right. So I ended. So I fixed the rational hull. So A is module finite of O. Because of that, I can speak about radicals. And now I also want to fix such a vector pi of sizes. And I can take such a matrix ring where I have A. So J is the radical of A. And the size of each square block is pi. So I have altogether R blocks on the diagonal. And, well, A and pi determine H. And now, results which were established by the Japanese algebraist Harada are the following. So firstly, the ring H I defined you before is a hereditary order. So it is an order and it is hereditary in the sense I already said. The center is the discrete valuation ring O I was starting with. And there are good uniqueness results. So if I have as a data A prime and pi prime, then the corresponding orders are isomorphic if and only if maximal orders are the same. And well, tuple p prime is a cyclic shift. Moreover, any hereditary order is isomorphic to the one from the previous slide. And there is also a nice description of the Jacobson heredity. For order H, on the diagonal I could have anything, but now on the diagonal entries belong to the heredity. And continuing, so knowing this, the semi-simple quotient of H is a product of matrix algebras, where again pi1 till pi r are entries of this tuple vector P, and D is determined by the maximal order A. So I take my maximal order, mod out the radical, the quotient is a skew field, not necessarily commutative. Again, it's some invariant attached to my data. So in general, the order I showed you need not be basic, but up to Morita equivalence, any hereditary order is isomorphic to this order HAE, where E is a tuple of ones. The number R, so the size of this matrix, is called type of hereditary order. So the type of hereditary order is actually the number of non-isomorphic simple modules of H. So it is invariant of an order. So I stated you the main results from the local theory. Now let me comment again how everything simplifies if I fill this algebraically. Again, in this case, there is a vanishing. Theorem of Witt says that the Brouwer group of the field of Laurent power series is U. And because of that, there are no non-trivial skew fields over L. And the former patterns becomes much easier. So any hereditary order up to Morita equivalence is isomorphic to the one written here. So no number theoretical effects. And this ring, moreover, can be understood in an equivalent language. Namely, this algebra is just zero completion of the path algebra of a cyclic quiver is R vertices. So a pattern which I think many people who worked in representation theory have seen many times. So algebraically closed field, things simplify again quite drastically. Now let me speak about Morita equivalences of hereditary curves. So I stated the result of Artin and de Jong for homogeneous curves. Hereditary curves are more general, and here is the result. So if I have one hereditary curve, then first of all, we can speak about the associated weight function, which attaches to every closed point x the type of the stock of the corresponding hereditary sheet H. So type is the number of pairwise non-isomorphic simple modules. For all points by finitely many, type is 1. So, and it is a property of this function rho. So if rho satisfies this property, it is 1 for all points by finitely many, then I call such a function weight function on my curve. And now a theorem which is due to Michael Spies tells that two such hereditary curves are equivalent if and only if centers are isomorphic. Again, like for homogeneous curves, I want the identification of Brouwer classes. but I also want the identification of the corresponding weight functions. So if it is fulfilled, then two categories of coherent sheaves are equivalent. Michael Spies is an algebraic geometer from Bielefeld, and his motivation came actually from the Langlands program. So I discovered relatively recently that hereditary curves, so actually non-commutative curves, appeared for the first time in the very first paper of Michel van den Berg and his advisor Freddy van Ostayan. I think it was his PhD project at the beginning of 80s. So at that time, it did not draw too much attention. So now things of course changed. But then in the middle of 90s, Stuhler from Göttingen came to the same idea that such objects can be useful. And then there is a very well-known paper of Stuhler, Rappaport, and Lamont, where these curves played a prominent role in the Langlands program, and they also played a role in the Fields medal work of Laforgue. And there was a question about equivalences of categories of coherent sheaves, which was fixed by Spies. Recently, with Drost, we proved a general result about Morita equivalences of arbitrary non-commutative schemes, in particular non-commutative curves. And from this general result, one can deduce special cases. Well, summing up so far. So when I want to define a complete hereditary curve up to a Morita equivalence, then I have to fix the central curve. I have to specify a Brouwer class, and the first two components define me homogeneous curve. But weight function allows me to define the hereditary curve up to Morita equivalences. So it is the data defining my categories. So now I think it's the time to speak about the result. So assume I have a data as before. So X is a curve of genus 0, a Brouwer-Savary curve. Assume I have an exceptional class eta. So it means that X and eta, they define a homogeneous curve, a non-weighted one. Assume I have a tilting object in a non-weighted. Then for any weight, I have a tilting whose tilted algebra is a so-called squid algebra of ring. Okay, so it is a result, maybe the main result of my today's presentation. Now maybe you are wondering what is pi and how to define pi. So I became interested in this theory about 5 years ago and started to read the corresponding literature, which was not so easy to follow because it was very non-geometric. When you ask, so what is pi, whatever, here I think the most transparent way to digest what we actually want, well, is as follows. So X and eta is our choice, fixing a homogeneous curve. And we said that eta is exceptional. So there is a distinguished exceptional object of Lenzing, given such a derived equivalence with a finite dimensional algebra lambda of this very special form. Now we have a weight function defining our non-commutative curve. So I make a list of all points for which I have weight at least 2. So for each of these points, I can take the corresponding simple sheaf, simple torsion sheaf, take its endomorphism algebra, which is some skew field. Now I take this sheaf as xi in the derived category and look at this image in the derived category of lambda. Then we know how it works for projective line. So in this generality, it's not much different. This T of xi is some regular module of a lambda. However, regularity is a notion to be discussed. So by some reason, I have to dualize to make from a left module, right module again. Okay, but what is here important, the data arising here are determined by my non-commutative. And now I wanted to tell you what is phi. So now I can tell you what is phi. Phi is a finite dimensional algebra given in the following matrix form. So I have lambda. So lambda is this hereditary algebra of matrices 2 by 2. On the diagonal, I have blocks. So di is endomorphism algebra of my simple regular module. And VI's are right modules of a lambda. So D1 is the endomorphism algebra of V1. V1 is a module of a lambda, right module. So again, we know how to multiply these things. And sizes of diagonal blocks, they are determined by my weight. So it is a definition of the squid algebra, or rather a version of it. Well, it is what it is. Yeah, at least I think one can understand what we do here. Right, so squid. So why it is called squid? You might ask. Again, things become more transparent if field is algebraically closed. Because there is only one Brouwer-Severi curve of an algebraically closed field. So there are no conics. It is only a projective line. The Brouwer group of the function field is 0. So there are no number theoretic effects. And there is only one minimal model for hereditary algebras, namely the path algebra of the conic. Yeah, we have this fundamental equivalence I started my talk with. So still to define a non-commutative curve, we might have a weight function which has a special locus. But of an algebraically closed field, so points have degree 1. So you can describe them tuples alpha and beta I. Under the Stilton equivalence, the image of the simple sheaf is this regular representation corresponding to alpha and beta I. It's endomorphism algebra is K. So the former algebra simplifies us a lot. So these di's are K's. Here we know what to write. Lambda is the path algebra of the Kronecker quiver. And everything can be written as a path algebra of a quiver with relations. And this quiver looks like as a squid. Yeah, so the name makes sense. So you see the body of the squid, it might be arms. Squids are closely related with canonical algebras. And again, if my field is algebraically closed, and canonical algebra is a path algebra of a quiver subject to these relations. So if I write quiver and relations in this form, that the corresponding ideal of relations is not missing. But still, it is the most transparent way to write the corresponding algebra sigma. So it is the canonical algebra, which all representation theorists in the audience definitely seen many times in their life. And the derived category of non-commutative curve, derived category of modules of a squid, and the derived category of the canonical algebra are all isomorphic. all equivalent. And the same thing is true of arbitrary fields. So it was a question how to define canonical algebras of an arbitrary field. And actually, of an algebraically closed field, so there is nothing, on my mind, there is nothing exciting about canonical algebras. So the notion is really interesting and deep if we omit this assumption on the base field. And then the definition was given by Klaus Ringel in 1990. And Klaus also gave the definition of a squid. However, I do not want to define the canonical algebras. So one observation I made when working on this project was that it is easy to define squid, but it is very challenging to define a canonical algebra in general in a talk, even to representation series. So it would need me quite a few slides to do it reasonably. Well, but still, here's a summary. So I want slowly to come to some conclusion. So an exceptional hereditary curve is given by the datum, curve of genus 0, projective, Brouwer-Severi curve X, exceptional class in the Brouwer group, and a weight. When is it a weighted projective line? Actually, if and only if X is projective line and Brouwer class eta is 0. So if not, then it is something else. And case B is automatic if our field is algebraically closed. Because firstly, there are no Brouwer-Severi curves but projective lines. And secondly, by vanishing of the Brouwer group, it is 0 automatic. And we have these equivalences of triangulated categories. Derived category of a non-commutative curve, derived category of a squid, and derived category. All right, so in the title, I've been mentioning orbifolds. Actually, it was indeed my intention to speak about the talk after I realized it's maybe indeed too much. But still, so let me summarize, or maybe raise your interest, well, to this part of the story. So actually it concerns equivariant sheaves on smooth curves. So I start with a smooth curve and a finite group acting on my curve, and I assume Maschke situation. The order of my group and the characteristic of my field are mutually prime. Well, I can take the quotient in the sense of schemes, and if y was regular, the quotient is regular. So basic algebraic geometry. But I also can take the so-called stacky quotient, and to make sense to the word stacky, I think the easiest way is to speak about non-commutative curve section. Namely, in the setting as above, I can define a sheaf H whose sections of any open subset of X are skew group algebras of these sections of my scheme Y with the group G. So if U in X is open and affine, so is the pre-image. Well, I have an action of my algebra of my group G on this algebra, and I can take this skew product. So I obtain a hereditary order H of U, and its center, well, so the ring of sections of my quotient X, which is not a ball. And it is a very well-known fact to the community, but still, so since I have not found a precise reference, I wrote arguments in my paper. Also, it's standard sheaf theoretic routine that equivariant sheaves on Y with respect to G are equivalent to the category of coherent sheaves on this non-commutative curve. And moreover, and it's actually important, that the Brouwer class of this curve is always zero. So it is some fact which follows from Artin's theory about invariants of a field with respect to a finite group action, and also some results about group cohomology in Brouwer. So it is standard, but maybe not entirely obvious. And now summary. So if I have a complete curve Y and a finite group such that the quotient has genus 0, then the category, equivalent category of coherent shifts admits it. And we have derived equivalences arising in this way. And in these terms, we, for instance, can, well, we get a proof of a result generalizing a theorem of Lenzing, and then Kirill of Polishchuk. I started my talk with. Yeah, and in particular, if Y is a projective line, field is algebraically closed, I have a group described by a Dinkin type, so I get this Mackay correspondence. Well, and another part of the story, which I like very much, but for which there is no time to deepen it, that there are very interesting examples. When we say our field is not algebraically closed, and the base field of real numbers is actually very interesting and deep. And in this case, there are very interesting finite group actions over reals on complex elliptic curves. So we can take a complex elliptic curve, and in this case, there are finite groups acting on them, but we have to view a complex elliptic curve as a real scheme. And such examples arise from wallpaper groups. So a nice story, maybe there will be once an occasion to speak about this. I would be happy to do it. It's all today. Thank you for your attention.
Thank you very much, Igor. That was a very, very nice talk, very insightful. Are there any questions? Frank has one.
Yeah, thank you very much for your very nice talk. I had a question about these orbifold cores. So you basically look at the quotient stack and look at the current sheaves over that. Is that how I should understand this?
Well, if you like stacks, so you are welcome to understand it in this way. But
Okay.
I prefer non-commutative curves.
Okay. Yeah.
So there is a question in the chat. So which papers are you talking about? So what I talk today about is my last preprint in the archive.
And I have a question about this algebra pi YG. Maybe
Yes.
you said what it is, but I didn't catch it.
Well, you have, so, oh, there are so many questions in the chat, but maybe
I think the others aren't questioned there. I think
well, so pi, you have to translate what it means in this generality. So you have to say what is pi in the setting when I have this very special non-commutative curve.
I see.
And I am precise in my paper when I speak about wallpaper groups which are related to automorphisms of elliptic curves. Well, but in general, one has to do some computations.
And if the field is algebraically closed, do you recover something that one might recognize? Yeah,
well, but then you get a canonical algebra, for example.
Oh, even in the case of the quotient.
Well, right. But the quite it's the most general thing what can happen.
Oh, I see.
And if you have a quotient, well, actually everything is very easy. So you have to look at those orbits where you have a non-trivial stabilizer. the stabilizer is necessarily a cyclic group. And here the length of this arm is actually the order of your group minus 1. So you speak about special orbits, so this pair alpha I, beta I tells you what is the orbit. Yeah, the orbit is projective line. So you say you have T non-trivial orbits. So for each non-trivial orbit, you have a special arm. So the order of stabilizer determines you the length. That's how you proceed. So it's not complicated of an algebraically closed field. And if you want not a squid, but something what Klaus Ringel like more, you tilt and get canonical algebra.
I see. Oh, very interesting. Yeah, I guess one has to study orders.
Absolutely.
Yeah. Okay, well, that was really a very nice talk. Are there any other questions?
Yeah, so if you take all these wallpaper groups, the classifications, so you will get for each case certain results which describes the current sheaves, or how?
Well, I mean, indeed, I mean, it's a very interesting story, indeed, because what we get there are the so-called real tubular curves. And the study was initiated by Helmut Lenzing and classification achieved by Dirk Hussin. And then just numerics indicated that those non-commutative real tubular curves coming from wallpaper groups are those curves for which my invariant eta is equal to 0. And those, yeah, right. So, no, even stronger. So these are tubular curves with commutative function field of my non-commutative. So they have their place in the classification very clearly and visibly.
Thank you.
Okay. There don't seem to be any other questions. So maybe once we've delved into the orders, we'll ask you for part 2. But I think it makes sense to sort of, look into that in more detail. But it's certainly very, very interesting. And there seems to be really a trend to study things over not algebraically closed fields. And I know that Calvin is very driven by that. So thank you, Igor. That was really very nice. And I hope that you and everybody else will have a nice holiday and a good start into the new year. So we'll see you at the end of January. I don't remember the date. 29th of January for a talk by
Anna Barbieri, I think.
Thank you, Anna Barbieri. Okay, teamwork. Excellent. Okay, so thanks everyone for coming, and Happy New Year. Well, Happy Christmas, Happy New Year, and see you in January.